This video is notes for determining limits analytically for math analysis students as an introduction to calculus. There are three ways to determine a limit: numerically using a table of values, graphically using a graph, and analytically. And analytically has more detail. We're going to start out using direct substitution. So the first limit I want to find, and I'm going to use direct substitution, is the limit as x approaches 4 of 3x minus 7. So what I'm going to do is I'm just going to plug 4 in for the variable x. So I have 3 times 4 minus 7, which is 12 minus 7, equals 5. So I have the limit as x approaches 4 of 3x minus 7 equals 5. And remember, a limit is not always what's happening at the point on the function. It's what's happening as you get close to the function. And if you can imagine what 3x minus 7 looks like, it's a line. It's a continuous function. There are no breaks. So all you're doing is looking for the limit as x approaches 4 of that function. You're looking for the y value. The second example we're using direct substitution is also something that's continuous, so that's why direct substitution will work. I want the limit as x approaches negative 3 of the absolute value of 4 minus 2x. So I'm going to have the absolute value of 4 minus 2 replace x with negative 3. So I have the absolute value of 4 plus 6, which is equal to 10. So the limit as x approaches negative 3 of the absolute value of 4 minus 2x is going to equal 10. And my last function using direct substitution is a rational function. 3x divided by x minus 1. And from Algebra 2, you should start to recognize these shapes and what they are. This is a rational function. The domain is going to be all real numbers except for 1. So this function is not continuous, but it's not continuous at 1. It will be continuous at 0. So I can use direct substitution, putting a 0 in for x. So I have 3 multiplied by 0 over 0 minus 1, which is going to equal 0 over negative 1, which is equal to 0. So the limit as x approaches 0 of 3x over x minus 1 equals 0. Direct substitution is always what you should check first, but there are other analytical methods, and these next examples are going to explain those. This next method we're going to use is factoring. And the reason I'm going to use factoring, if I put a 2 in for x in direct substitution, I get 2 minus 2, which is 0, and 2 cubed minus 8. 2 cubed is 8. 8 minus 8 is 0. I would have 0 over 0. So I cannot do that. So I'm going to use factoring. So I have the limit as x approaches 2. The numerator cannot be factored at it's x minus 2. The denominator can be factored. This is a difference of cubed. So we have x minus 2, x squared plus 2x plus 4. Common factors. X minus 2 over x minus 2 is 1. So I'd have the limit as x approaches 2 of 1 over x squared plus 2x plus 4. Now I can use direct substitution. So I'd have a 2 in for x. Actually, I don't need parentheses around there. Let's get rid of that. This is 4, this is 4, this is 4. 4 plus 4 plus 4 is going to be 12, so this would be equal to 1/12. So the limit as x approaches 2 of x minus 2 over x cubed minus 8 is going to equal 1/12. The next method, the next problem I'm going to do is still factoring. Same thing, I would always try direct substitution first. So if I put a 0 in for x, I'd 0 plus 0 plus 0, which is 0. 0 plus 0, which is 0. So I'd have 0 over 0. So I'm going to go ahead and factor. So I'd have the limit as x approaches 0. I can factor greatest common factor out of the numerator. and I can factor greatest common factor out of the denominator. Well, right away I notice the common factor x I can get rid of. If I plug, I could actually plug a 0 in for x at this point. 0 squared, 0, plus 4 times 0 is 0, plus 4 over 0 plus 2. So I'd have the limit as x approaches 0 of x squared plus 4x plus 4 over x plus 2 would be 0 squared plus 4 times 0 plus 4 over 0 plus 2, which is equal to. So the limit as x approaches 0 of x squared plus 4x plus 4 over x plus 2 equals 2. And when I wrote this problem, I first looked at this and said, well, we could factor this twice. X squared plus 4x plus 4 is going to be x plus 2 multiplied by x plus 2. My numerator and denominator, I could get rid of an x plus 2. But in this case, I didn't need to. As soon as I got it down to where I could plug in a 0 and get a number, that's what I did. My last problem for factoring, if I put a negative 1 in for x, I get negative 1 squared, which is 1. 1 minus 1 is 0. Negative 1 squared plus 4 times negative 1 is negative 3. Negative 3 plus 3 is 0. So this again gives me 0 over 0. So I'm going to go ahead and factor. I'd have the limit x approaches negative 1. My numerator is a difference of squares. My denominator is going to be a trinomial. Common factors are this x plus 1. So I have the limit as x approaches negative 1 of x minus 1 over x plus 3. Now when I do direct substitution, I'm going to put a negative 1 in for x. This will be a negative 2 in the numerator and a 2 in the denominator, which is equal to negative 1. So the limit as x approaches negative 1 of x squared minus 1 over x squared plus 4x plus 3 is equal to negative 1. And it's good to get in the habit of every single time that I've manipulated this, I've written limit in front of the function. Once I started plugging in the value, I didn't write limit anymore, and that's what I would expect of my students. There's another technique analytically that I want to show you. And we're going to be doing rationalizing the numerator. When you're rationalizing the numerator, it's because if you put a 0 in for x at this point, 0 plus 1 is 1. Square root of 1 is 1. 1 minus 1 is 0. Put a 0 in for x, I get 0 in the denominator. So I get 0 over 0 again. So what I want to do is rationalize the numerator. If you think back to Algebra 1, most of you learned how to rationalize denominators, and it was really just cleaning up a problem. Now we're going to actually use that technique. So what I'm going to do is I'd have the limit as x approaches 0, square root of x plus 1 minus 1 over x. I'm going to multiply it by the conjugate of the numerator. So I'm going to have the same terms, but instead of a minus here, I'm going to use the opposite sign, a positive one. But in order to multiply and not change the value, I'm going to multiply the same numerator and denominator by the same thing. And that is saying I'm multiplying by 1. It's the multiplicative identity property. So when I multiply, I'm just going to be very careful. The square root of x plus 1 multiplied by the square root of x plus 1 is going to be x plus 1. The square root of x plus 1 multiplied by a positive 1 is going to be plus the square root of x plus 1. Negative 1 multiplied by the square root of x plus 1 is going to be minus the square root of x plus 1. And negative 1 multiplied by positive 1 is going to be negative 1. My denominator I'm not going to multiply out. You're going to see in a minute, it actually comes out a lot easier if I don't multiply it. These middle terms, the square root of x plus 1 is positive, and this is a negative square root of x plus 1. You add those together, you get 0. You get a positive 1 and a negative 1. That adds to 0. So I would have the limit as x approaches 0 of x over x multiplied by the square root of x plus 1 plus 1. Now you can see why I did not multiply these x in, because if I have an x divided by an x, that's equal to 1. So this would be the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. Now when I substitute a 0 in for x, the square root of 0 plus 1 is the square root of 1. The square root of 1 is 1. So 1 plus 1 is 2. So my answer is going to be 1/2. So the limit as x approaches 0 of the square root of x plus 1 minus 1 over x is going to equal 1/2. One more example in rationalizing a numerator. This one's a little bit different if you look. This had the square root of x plus 1 minus 1. This is going to be 4 minus the square root of x. It's going to still be the same process. I always check first, plugging in the 16. 4 minus the square root of 16 is 4 minus 4, which is 0. 16 minus 16 is 0, so I have 0 over 0 again. So I'm going to multiply by the conjugate of the numerator. So I have 4 plus the square root of x. Make sure I multiply numerator and denominator by the same term. So I'm multiplying by 1. And it's the exact same term, but this is a minus sign, so this would be a plus. If this were a plus sign, this would be a minus sign. So I'd have the limit as x approaches 16. 4 multiplied by 4 is 16, plus 4 square roots of x, minus 4 square roots of x, and a negative square root of x times a positive square root of x is minus x. Once again, I'm not going to multiply my denominator together. You're going to see why in a minute. So the positive 4 square roots of x and the negative 4 square roots of x is 0. So I'd have the limit as x approaches 16. 16 minus x over x minus 16, and then the square root, 4 plus the square root. Clean that up a little bit better. Four plus the square root of x. When I teach Algebra 2, I get the students to do this a lot in factoring. They should be able to recognize 16 minus x and x minus 16 are not the same thing. This 16 is positive, this 16 is negative. This x is negative, this x is positive. So I need to do a little bit of algebraic manipulation. One of my favorite things about math is we can manipulate things. If I factor out a negative 1, it's going to make this a negative 16 and a positive x. So I'm going to put this as x minus 16 so you can see this easier. Rewrite everything else. And I always double check by multiplying. Negative 1 multiplied by x gives you my negative x. Negative 1 multiplied by negative 16 gives you my positive 16. What this does now is I can get rid of the x minus 16 in the numerator and the denominator. So I'd have the limit as x approaches 16 of negative 1 over 4 plus the square root of x. Now I'm going to plug the 16 in for x. So I get negative 1 over 4 plus the square root of 16. The square root of 16 is 4. 4 plus 4 is 8. So that equals negative 1/8. When I rewrite it, the limit as x approaches 16, 4 minus the square root of x over x minus 16 is going to equal negative 1/8. These problems aren't difficult. You just have to go slow and be careful. The last technique I'm showing you is determining a limit analytically using a common denominator. Students don't like these problems typically, and it's mainly because of fractions. It has nothing else to do with the math or the calculus. The calculus behind this is easy. It's really just because there's fractions. I have 1 over x plus 2 minus 1 over 2. My common denominator is going to be 2 multiplied by x plus 2. So when I rewrite this, I'm going to have the limit as x approaches 0, 1 over x plus 2. I'm going to multiply this by 2 over 2. Then I have minus 1/2. I'm going to multiply this by x plus 2 over x plus 2. And I'm just going to use parentheses here to clean it up. And this is all divided by x. Now I'm just going to go ahead and multiply carefully. When you're multiplying fractions, you're going to multiply numerator times numerator. So I have 2 times 1 is 2, 2 times x plus 2 is 2x plus 2. I'm not going to multiply the denominator. When I multiply my numerators, 1 times x plus 2 is going to be x plus 2, and then 2x plus 2. And I'm dividing everything by x. So the limit as x approaches 0, I'm subtracting all this. 2 minus x minus 2 over 2x plus 2. I'm dividing by x. So I'm going to put a division symbol here and write the x. My next step, limit as x approaches 0. 2 and a negative 2 is 0, so I have negative x over 2x plus 2 times 1 over x. Now I can see I can simplify this a little bit better. I have a negative x in the numerator and a positive x in the denominator. So that means it's going to give me negative 1 in the numerator. So the limit as x approaches 0, negative 1 over 2 multiplied by x plus 2. That's the simplest form that I can get that into. When I put a 0 in for x now, 0 plus 2 is 2. 2 times 2 is 4. So this is going to be equal to negative 1/4. So the limit as x approaches 0, this whole term, 1 over x plus 2 minus 1/2, all divided by x, is equal to negative 1/4. So once again, writing neatly, going slowly, it's not a hard problem to do. You just have to be very careful. And the last example I'm going to show you is very similar, just to give you one more example. I have got the limit as x approaches 0, 1 over x plus 5 minus 1 over 5, all divided by x. My common denominator is going to be 5 multiplied by x plus 5. But I'm going to make this a little bit shorter this time. So the limit as x approaches 0, 1 over x plus 5, I'm going to multiply that by 5 over 5. Minus 1 over 5. And I'm going to multiply that by x plus 5 over x plus 5. And that's all being divided by x. Well, I should have mentioned also, what I should first do is put a 0 in for x. If I put a 0 in for x, I get 1/5 minus 1/5 in the numerator, which is 0, and 0 in the denominator. So this is why I'm doing this technique. Then I'd have the limit as x approaches 0. 1 times 5 is 5. My denominator is 5 multiplied by x plus 5. Minus 1 times x is going to be minus x. Minus 1 times 5 would be minus 5. And remember, I'm dividing by x, so I'm multiplying by 1 over x. So that would give me the limit as x approaches 0. Give me negative x over 5 multiplied by x plus 5 times 1 over x. The negative x and the positive x gives me negative 1, so the limit as x approaches 0, negative 1 over 5 times x plus 5. Plug the 0 in for x at this point, I get negative 1 over 5 multiplied by 0 plus 5. This would be negative 1 over 25. So my answer would be the limit as x approaches 0 of 1 over x plus 5 minus 1 over 5 divided by x is going to equal negative 1/25.